All right, let's dive right into one of the biggest, weirdest questions in all of physics. And I mean, this is a mystery that gets right down to the very stuff you are made of. Me, the planet, everything. So here's the question. Why are there three versions of you? Yeah, I know, that sounds completely bizarre, but stick with me. See, at the most basic fundamental level, everything is made of just a few tiny particles. But here's the kicker. For some reason we absolutely cannot explain, nature went and made three nearly identical copies of the whole set. Physicists call these copies families or generations. A good way to think about it is like having three different, complete sets of Lego bricks. Each one has all the pieces you need to build an entire universe. So check this out. In that first column, you've got generation 1. This is our home turf. These are the particles that build pretty much everything we see. You've got your up and down quarks making protons and neutrons, and of course, the good old electron. These are the stable, everyday workhorses. But then you look at generations 2 and 3, and they're just copies, duplicates. They have the same charges, the same properties, except for one really, really weird difference. And that one difference, well, that's where we get to the real heart of this whole cosmic puzzle. Because these aren't just random copies. There's a pattern to them, and it is seriously strange. Okay, so here's the deal. Each new generation is way heavier and way more unstable than the one before it. The particles from the second and third generations, they pop into existence and then poof, they decay back into the stable generation 1 particles almost instantly. They're like these fleeting ghosts of matter only showing up for a split second in really high energy places, like when a cosmic ray smashes into our atmosphere or inside our most powerful particle accelerators. And when I say heavier, I mean it's just staggering. Let's just look at the electron and its heavy cousins. So you've got the electron. Let's call that our baseline. Then you have the muon from generation 2. It's over 200 times heavier. And then the tau from generation 3, it's almost 3,500 times heavier than an electron. It's like having a house cat, a grizzly bear, and a blue whale, but claiming they're all the exact same animal in every other respect. It just doesn't make sense. So this leads us to the big, flashing billion-dollar question that has kept physicists up at night for decades. Why? Why would the universe bother making these ridiculously heavy, super unstable copies of particles that were already working perfectly fine? I mean, our entire visible universe runs on just generation 1. What's the point of the other two? It feels totally redundant. Well, there's a fascinating new idea on the table. It's speculative for sure, but it offers a kind of mechanical explanation for this whole mystery. And it suggests the answer is woven into the very fabric of space-time itself. Okay, so this idea is called the carrier ball theory. And here's the gist. Imagine the universe is an empty space, but is actually made of some kind of fundamental fabric. Now, in this picture, a particle isn't some tiny little dot. Instead, it's more like a vibration, a resonance that's living on a little deformation in that fabric. And they call that deformation a carrier ball. So you might be asking, how does this actually make a particle? Well, it goes something like this. First, you get a deformation in this universal fabric that creates the carrier ball structure. Now, the more energy you pour into that one spot, the bigger the ball gets. And here's the crucial part. The final size of that ball and how stable it is what decides what kind of particle you end up with. And that one simple concept, that size is everything, might just be the key to cracking this whole 3-generation puzzle wide open. So here's how it all connects. According to this theory, the smallest carrier ball you can make, the one that needs the least energy, is also the most stable. And that gives you generation 1, the electron. Now, if you pump in more energy, you can make a medium-sized ball. It's less stable, and presto, you've got generation 2, the muon. And if you pump in the most energy, you get the largest possible ball. It's super unstable, and that's generation 3, the tau. Suddenly, it's not about 3 random copies anymore. It's about 3 different, distinct sizes of the same underlying structure. It all clicks into place. But you know, like any good scientific explanation, this one immediately makes you ask another question. It's a really neat answer for why the generations have different masses, but there's still one little loose end hanging there. And the puzzle is this. If the particle's mass just depends on the size of this carrier ball, then why shouldn't there be a particle for every possible size, right? Why don't we see a smooth continuum of masses instead of these 3 very specific, separate steps? Well, the thinking goes, the suspicion, is that this quantized behavior, this jump between three specific levels, is because only those three particular sizes are stable enough to even exist, even for a fraction of a second. Anything in between is just fundamentally unstable and can't form a particle at all. So it's less like a volume dial that you can turn up smoothly and more like a gear stick with only three distinct gears: 1, 2, and 3.
Now, of course, we've got to remember this is still a theory. It's a really elegant picture, it's compelling, but like any big idea in science, it's got to face the music. It has to be tested. And it's only going to be future experiments pushing the limits of physics at the highest energies that will tell us if this idea actually holds water.
And that really leaves us with something to chew on, doesn't it? This whole mystery of the three generations is a perfect reminder that there are these incredibly deep, fundamental rules to our reality that we're only just beginning to get a handle on. It just makes you wonder, what other huge cosmic rules are out there, hiding in plain sight, just waiting for us to find the right question to ask?